Have you ever stopped to look around and just wonder? The phone in your hand, the car on the street, even the coffee in your mug. None of it just appeared. Behind every single one of those things is a plan, a kind of universal blueprint that engineers use to build our world. And today, we're going to learn how to read it.
First things first, we've got to learn the lingo. You see, engineers have this special way of looking at the world. It lets them take any process, no matter how huge or complicated it seems, and break it down into a simple, solvable puzzle.
Seriously, how does that happen? It feels like magic, but it's not. It's a system. And that system is built on just a few core ideas that, once you get them, I promise you are going to start seeing them absolutely everywhere.
So, imagine you're an engineer staring at a massive, sprawling factory. Pipes and tanks everywhere. Where in the world do you even start? Well, it turns out they always begin by asking one simple, powerful question that splits everything into two main categories.
It's called process classification. You know, it's kind of like dumping a 1,000-piece jigsaw puzzle onto a table. What's the first thing you do? You find all the edge pieces, right? You have to sort out what you're dealing with before you can even begin, because that first choice changes all the rules for what comes next. And here are our two piles of puzzle pieces, batch and continuous. A batch process is just like baking a cake. You put all the ingredients into the bowl at the start, you mix it, you bake it, and then you take the finished cake out. Nothing else goes in or out while it's in the oven. A continuous process, on the other hand, is more like a river. There's a constant flow of water coming in upstream and flowing out downstream.
And you can spot these all over the place. Doing a load of laundry, that's a classic batch process. You load it, you run it, you unload it. But what about a pressure cooker that's slowly letting off steam while it cooks? That's what we call a semi-batch, because something is leaving mid-process. And that huge oil refinery running 24/7? Oh yeah, that's the textbook definition of a continuous process.
Okay, so once we know what kind of process we're looking at, we get to pull out the single most important tool an engineer has. It's one equation that works like a universal law of accounting for, well, pretty much everything.
And this isn't just, a helpful guideline. It's a non-negotiable law of physics. If your design doesn't satisfy this balance equation, it's not that it's a bad design. It's that it physically cannot work. It's the ultimate reality check.
Now, the equation starts off really simple, totally intuitive. You just track what comes into your system, and you subtract whatever goes out. Makes sense, right? Stuff can't just disappear into thin air.
But here's the full picture. We also have to account for anything that gets created, that's generation, or anything that gets used up in a chemical reaction, that's consumption. You add and subtract all those things, and it all has to equal accumulation, which is just a fancy way of saying any change in the amount of stuff that's stockpiled inside the system.
Now this leads to a super useful shortcut called steady state. Think back to that factory that's running smoothly, 24/7. Nothing's building up inside the pipes, nothing's running dry. That means the accumulation is zero. And suddenly our big equation gets way simpler. It just becomes everything going in must equal everything going out.
All right, so we have the core concepts. We have the master equation. But how do we organize all this for a real problem without our heads exploding? Simple. We draw a map. We create the blueprint.
And here's how you do it. First, you just draw a box for each piece of equipment, your mixers, your heaters, whatever. Then you connect them with arrows, which are the streams of material flowing between them. You label everything you already know, and for everything you don't know, you give it a symbol, like X or M.2. And just like that, you've got a visual guide to your entire problem.
Okay, theory time is officially over. Let's put all this stuff into practice. We're going to use our brand new toolkit, the classification, the balance equation, and the flowchart to solve a real problem from start to finish.
So here's our mission. We have a stream of olives, 10 kilograms worth every single second, flowing into a machine called an extractor. We're told these olives are 10% oil by mass. The machine does a perfect job of separating them. The question is, how much pure oil and how much solid stuff comes out the other end?
Okay, and here's our flow chart, our blueprint. One stream going in, that's our 10 kilograms per second of olives. It goes into the extractor box, and two streams come out. One is pure oil, and the other is pure solids. Our job is to figure out the numbers that go where those two question marks are.
Now, it's time to think like an engineer. We have options here. We could write a balance equation for the total mass going in and out. Or we could write one just for the oil, or one just for the solids. What do you think is the smartest place to start?
Here's the pro move.
You always start with the balance that has the fewest unknowns. If we look at the total mass balance, we have two things we don't know: the oil stream and the solid stream. But if we do a balance on just the oil, there's only one unknown in that equation. That's our key. That's our way in.
So let's do it. Let's do an oil balance. We know 10 kilograms per second of olives are coming in, and we know 10% of that is oil. So the amount of oil coming in is 10% of 10, which is 1. That's it. That means 1 kilogram of pure oil must be coming out every single second. Boom! First unknown solved.
And once you have that first piece, the rest is easy. We could do a solids balance. 90% of the 10 kilograms coming in is solids, so that's 9 kilograms coming out. Or, even simpler, we can just look at the total. If 10 kilograms go in and we already know 1 kilogram of oil comes out, well, the rest has to be the solids, right? 10 minus 1 is 9. The blueprint works.
So we just solved the problem for one little extractor, but the real magic here is that this exact same way of thinking, this blueprinting process, is how you design and troubleshoot entire factories. It all scales up.
The best way to think about it is like they're Lego bricks. You have a mixer brick that combines your flour and sugar. Then you have a reactor brick, like an oven, that uses a chemical reaction to turn dough into cookies. Then you could use a separator to pick out the burnt ones. By connecting these simple, fundamental blocks, you can design a process to make literally anything.
So the next time you see any product, don't just see the finished thing. Try to see the blueprint behind it. Think about the inputs and the outputs, the reactions and the separations. Now that you can speak the language, what hidden factories are you going to start seeing in your everyday life?